My name is Zhongyan Zhao. In this talk, I will present our paper on distributed link sparsification for scalable scheduling using graph neural networks. This is a collaborative work with Anthony Swami and Santiago Segarra. In this talk, we address problems in wireless multi-hop networks. The key feature is that the nodes in the networks are autonomous and self-organizing, which means that there is no base stations to allocate resources such as routing, scheduling, power allocation. All those functions has to be done by the users or the nodes themselves in a distributed manner. This type of network has a long history in military ad hoc networks. Recently, it becomes more relevant in 5G and beyond. First, I will introduce some basics on distributed scheduling. The first concept is conflict graph. So a vertex in the conflict graph represents the link in the wireless network. If two links has an edge between them on the conflict graph, that means there are some conflict between these two links. In this case, these two links share the same user, and this user can either talk to this one or this one. Therefore, these two links cannot be turned on at the same time. Another type of conflict is interference. In this case, these two links, they are close to each other, so if they turn on at the same time on the same channel, they will block out each other. Another concept is orthogonal access, which basically says that if this link is scheduled, then its immediate neighbor on the conflict graph shall not be scheduled. So most of the distributed scheduling is contention-based. The contention can be viewed as a process of a nodes comparing its number with its neighbors. This number could be utility in the case of distributed greedy scheduler, which is for synchronized network. So basically, they need to exchange their numbers with the neighbors. Obviously, the more neighbors you have, right, the higher the scheduling overhead is. And this number could also be random numbers in the case of CSMA. However, the more neighbors you have, the more likely some of your neighbor will generate the same number with you, which will cause a collision. When that happens, everybody needs to do the contention again. That's also higher overhead. With more and more wireless devices are now connected, the network density increases, so as the overhead. As we can see the trend that from a sparse to massive access, the overhead will actually take up all the radio resources. And in the process, the network capacity will be decreased, the battery life will be decreased, and the radio footprint will increase. This means the more security and vulnerability as well as interference. To address these problems, existing solutions such as topology control, it could reduce the transmit power so that the interfering neighbor is reduced. This approach has limitations such as increased hop distance between source and destination. This means longer latency as well as the overhearing. Another one is the sleep scheduling, which puts nodes into periodical sleep so that at a given time there are less active nodes in the wireless network. This approach, however, only applies to sensor networks where the traffic demand is very low. For cross-layer optimization, you jointly optimize the transmit power and many other parameters at different layers. It can improve these performance, but that only works for sparse networks because it requires information exchange between nodes and its neighbors. So this involves actually high overhead. What we want to focus on is the fourth method, the traffic-based link sparsification for general networks, general traffic types. The basic idea of traffic-based link sparsification is that we only let the most demanding links contend for scheduling. So here the demand is quantified by per link utility. And we assume that we know the distribution of the per link utility, such as here. And then we have a cutoff quantile eta. For example, if we want to cut off 95% of the links in the network. Then we set this eta as 0.95, then we get a threshold of utility. And then with this link specification function, which basically in the if-else form says that if the utility is smaller than the threshold, we will cut off this link from contention. Then we can reduce 95% of the links and reduce the density of the conflict graph to only 5%. However, this approach has some drawbacks. First, it has a longer backlog. Here, notice that this utility is proportional to the queue length, so that we can only be get scheduled if we have a longer queue. The second drawback is the loss of network capacity. For example, in this conflict graph, right, we have these utility numbers, and then we have this threshold of 10. So only these three links in blue will be scheduled, will be content for scheduling, and with a greedy scheduler, this one will be scheduled. And notice that we miss this opportunity, so that we lose some capacity in this case. So the question is, can we do better than this statistical thresholding? What we come up with is a localized function, which is modified from the statistical baseline. So here we introduce two additional parameters, z0 and z1. We call this link parameters. So the link parameters can set different local thresholds for different links. For example, for this peripheral link, we can reduce its local threshold so that it's more likely to be scheduled. For this for the central link, we can increase its local threshold so that it's less likely to be scheduled. In this way, we leverage the topology of the network to improve the total utility as well as the overhead. Now the question is how to generate these link parameters. Obviously, the topology of the network will changes from time to time because we're working on wireless networks. Therefore, we use graph convolution network to generate these link parameters. GCN can be implemented in a distributed manner. So when it's implemented in a distributed manner, the local computation and communication cost is only proportional to the local neighborhood of a node. So this node only needs to be communicated with its own neighborhood for L rounds, given an L layered GCN. In this way, the cost is reduced compared to other methods such as distributed optimization, which usually needs thousands of rounds of communication. Also notice that the GCN only need to run once a while, because we don't want to update this Z for every time slot. Instead, we may only need to update them Z for every hundreds of time slot. Right. So now the whole process looks like this. Originally, we directly put the conflict graph into the scheduler, which you call this dense scheduler. Now, we first put this conflict graph into a link specification function H, and we get a sparsified conflict graph, which is then put into the scheduler, which we call this whole process as a sparse scheduler. Notice that our pipeline is non-differentiable. So here we have a link specification that is not differentiable because of that step function. We also have this contention process, which is also non-differentiable. However, look at our objective function for optimization. We want to maximize the total utility of schedule, and we want to minimize the overhead, which is the number of edges in the sparsified conflict graph. Both of them are output of the non-differentiable functions. So this makes the training of our GCN extremely difficult. To train the non-differentiable downstream pipeline, we developed a two-stage reinforcement learning scheme. So you can read the paper for more details. And here I will only mention the intuition between these two stages. For stage one, we try to get the topological selectivity of the GCN Basically, we want to get higher utility with less nodes. Right, for stage 2, we actually reduce the number of edges in the sparsified graph. To do so, we normalize these link parameters generated by the GCN from stage 1. In this way, we can get a lower utility, that is approach to the statistical baseline. We also, on average, we will get the average local threshold to be close to the global threshold. As you can see from the figures, here for the orange curve shows the end of stage 1. We have higher utility compared to the end of stage 2. However, look at the number of nodes and the number of edges. For stage 2, we can really reduce them to the desired level. Now let's look at the performance of our approach. So the first experiment, we draw network state that include graph and the utility vector from a desired distribution. We put this network state into 3 different schedulers, a dense scheduler and 2 different sparse schedulers. What we present is the relative performance of the sparse scheduler to the dense scheduler. Basically, the sparse scheduler normalized by the dense scheduler. As we can see that on the total utility, the GCN-based approach can achieve higher total utility than the statistical baseline. Here the x-axis is different cutoff quantiles. And also, when we look at the average degree of the sparsified conflict graph, the GCN reduces the average degree, which means less collision rate in a random access network. For synchronized network, GCN also reduces the message complexity in the scheduling process. The second experiment, we run simulations on scheduling. So the difference is that for the previous experiment, the input state is the same. Now, for real scheduling, the input state for different schedulers are usually different because the utility depends on the queue length, and the queue length involves based on the decision of schedule. So in this experiment, we are working on medium-sized network with 1 to 300 links, and we have 500 different conflict graphs. And these results are averaged over these 500 graphs, and for each instance there are 300 time slots. So we can see that with GCN-based approach, we can reduce the average degree of sparsified conflict graph to only 1/3 to 1/5 of the statistical baseline. This means that for random access network, our GCN can achieve only 1/3 or 1/5 of the collision rate. And for synchronized network, we look at the point-to-point message complexity for the scheduler. But we can see that for denser networks, our GCN can reach lower overhead, and this is what we really desired. Here, notice that the cutoff quantile is 0.95, which is a very high number for cutoff. In conclusion, in this work we presented graph-based link sparsification to reduce the scheduling overhead. So we do so by exploiting the network topology by introducing localized link parameters. And our approach can generalize to different topologies with very low computational and communication overhead. In the future, we plan to develop a more principled approach for learning on non-differentiable pipeline. Here's the reference of this work. This is the end of this talk. Thank you for your attention. You're welcome to leave your comments or send us email. Bye-bye.